Hello, today I will be talking about inverse treatment planning using a virtual treatment planner, VTP, for prostate cancer treated with an intensity modulated radiation therapy, IMRT. IMRT is a way of another type of external beam treatment where basically we know what we want the dose here to be. So we'll inverse weight. So we'll weight this and then we'll weight the actual beam. The beam's divided into different pixels, also called beamlets. So in commercial available use, they used dose to volume histogram based optimization, which is basically this chart graph here, where the X is dose. It's in percentage, so 100 would be actually the dose, the prescribed dose of 79.2 gray. Here's the volume percentage, the volume that gets that dose. In a clinical routine, a amateur operates a TPS to attain an optimized plan via addressing the TPPs, which in our case, since we're doing prostate cancer, you have your PTV, you have your target volume, which is planning target volume. You have your organs at risk. For us, that is the bladder and rectum. The weights for those organs, the dose constraints for them, and the irradiated volume are what can be tuned. To generate a clinical acceptable plan, the process can be tedious, and it changes in with one, the time that the planner has to plan, and also the experience of that planner. We propose to build a virtual VTP that can interlocally operate in the commercial TPS for treatment plan optimization. With the aim that they can behave like a human planner. So basically, we wanted to follow this kind of flow chart where it starts, initialize the parameters, optimization engine. It'll go through the here. If the plan's okay, yes, or if it hits the maximum number of steps. If not, it will continue this loop. We propose the VTP with an end-to-end deep reinforcement learning base, which can learn from the environment, optimize its parameter adjusting policy through training deep neural network. We use the Q learning framework. The training could be low efficiency due to the frequency sparse matrix operation. To overcome this, we use PYCUDA that allows us to switch the optimization from CPU to GPU to speed up the training. The network structures are shown here in figure 2. There's 9 of them to represent the parameters that it can tune. It uses an epsilon-gradient algorithm, which basically in the beginning, it will give whatever has the greatest improvement. After it'll decay over time, and it will use more of a knowledge-based. The test bed we used was IMRT for prostate cancer. The training, verification, and testing for the VTP consists of 10, 2, and 50, respectively. Our initial for the 10 training cases was about a 5.5. But once the VTPN was able to tune, it reached up to an 8, which is almost a perfect score of 9. We quantified the plans by using the ProKnow system, which gives a 1 for each dose constraint that it satisfied. There was 8 for the OARs and 1 for the PTV. We got for the 50 training cases, we started at a 6 and then went up to an 8. If you look over here, this shows a training case. As you can see, the blue is bladder and the black is rectum. At the beginning of both of these, this B is actually for testing. Both did poor with the OAR sparing. As you can see, there's high dose in both of them. In step 1 up here, they actually did evaluate the bladder more than the rectum, but put too much dose in the rectum. So this fails and it's not usable. Here, it just tighten up the drop a little bit of the shoulder. In step 8, both of them made the same error where it valued the OARs too much and put too much high dose. That's where you see this bright red. But then in step 14 here and step 12 here, they both reached a optimal perfect score of 9, where you can see there's good sparing to the OARs and good dose coverage of the PTV. These graphs right here show how the weights, each one tunes as it goes through. Next, I'll be talking about the time performance. The statistical study. This first graph, figure 4, shows you the groups divided by their initial plan score and with the medium and standard div. As you can see, it does a great job of taking lower ones to higher plan scores. Then for step figure 5, this is the time performance one I was mentioning earlier, where we moved the optimization from CPU to GPU based. This was divided up by the top 5 most ran functions of the CPU. And as you can see, there was quite improvement in time deterioration. The proposed DRL-based VTP was able to operate the Eclipse-equivalent dose engine to generate high-quality plans for prostate. The future work will be focused on improving the network performance with more patient data testing and further training. And we also want to eventually connect the VTP into the Eclipse Research Station via Eclipse Project Application Program Interface (API) to further improve the robustness of the network and actually using the real treatment planning environment. Thank you.